Good morning, everybody. Hope you're doing all right out there. This is the final stream uh, on our ecology unit, and then you can focus in on physics for the rest of the time. This weekend, you can spend doing the ecology assignment that I just posted. And that's about it. So hopefully this won't be a too long stream because there's only one little section here left to do. And so first we're going to go through these questions and see how that goes. So yesterday we were talking about limiting factors, things that limit a population's ability to reproduce and survive, and its population, what sort of limits there are on its population. So let's see what these questions say. So reindeer were introduced to a northern island where they fed on moss and lichen. There were 24 females and 2 males. In the next years, the population would double from year to year uh, from the year before. So we went 24, then we had 48, then 96, 192, etc. But the population suddenly crashed down from almost 1,000 to 28, and then to 3, and then to 0. So why did the caribou population increase so quickly? So in this case, we want to think about the properties that control a population. So we have factors that affect population, and we want to think about these 4, right? So the birth potential, capacity for survival, procreation, length of reproductive life. So those are some things to think about. And then the limiting factors. So carrying capacity. Yeah, okay. I think we can make it up from there. So why did the numbers increase so rapidly? Sorry, my typer doesn't want to work here for a second. Okay. Oh, I know. Just 1 second. Okay. So the caribou, or the reindeer here, why did their numbers increase so quickly? So early on, there there were minimal limiting factors on the population. They had essentially all the food they could need. They had unlimited food and no predators and no competition for mates. And so what happened is that the reason they died out by our ecology terminology, that's fun. The reason they died out is because they exceeded the carrying capacity of the island. The island could no longer support such a large population, and there were not enough resources to sustain the reindeer. All right. So hopefully that makes sense. We essentially have an island with a limited amount of maybe we need to get rid of that unlimited. They had food. They have enough food and no predators and no competition for mates. And so when they exceeded the carrying capacity of the island, then they would have an ecological crash. Bird watchers often feed birds in the winter. One bird that is popular at feeding stations is the cedar waxwing. Does feeding the birds change the carrying capacity of the waxwing population? So this is a sort of a thinking question. You can write whatever kind of answer you want. I might argue that it does, right? It depends how much you're feeding them, but if the waxwings do depend on the food, so let's say, yes, if the waxwings depend on uh, the feeders as an essential food source, then the population can be larger due to this additional resource. I'm gonna put a little can depend on it because I know I don't fill my bird feeder very often, so I don't think my birds can depend on it. So sometimes it's a nice treat to them. Sometimes if you actually have a regularly filled bird feeder, then the population actually can increase in size. So why would there be an increase in falcon number? Hopefully this would be obvious that by increasing the carrying capacity for waxwings, the falcon population will have a similar increase in size as these are one of its food sources, as the waxwings and so the waxwings are now more available to there are now more waxwings because by feeding them we increase their capacity to survive. And so now that there are more waxwings, there can be more falcons. That's pretty cool. And this is also another interesting reason why we might want to protect something simple, like say, what was it? A couple of years ago, we had that small wetland in Winnipeg that that they ended up paving over. What was that called? It's only last year, wasn't it? It was over by Waverly and Wilkes. Um, Anyways, it was a disputed territory there that they wanted to preserve, and then the developer came in and he cut down all the trees. Well, I mean, those small environments might be supporting a bunch of low trophic level organisms, and then the larger or the higher trophic level organisms, like the hawks and the falcons and things, they are depending on those small pools of animals um, to provide food to support these higher levels. And the higher levels do have to eat a lot to get energy. So we do have to think about how we're going to protect our small environments, not just our large ones. Okay. So here's some extra definitions thrown in for you. So recall these definitions: ecosystem, biotic factors, abiotic factors, community, population. So just a little reminder, it's been a little, we're in the back end of the book. So abiotic and biotic factors affect all living things. Abiotic factors like air quality, climate, weather, nutrients, etc., have an effect upon all the living things in the area. And then biotic factors will affect living things as well. A mouse is affected by predators, by the available food, and by competition from other mice. The number of mice then affects the number of foxes. If the number of mice changes because of the available food, the number of foxes may change. These population influence each other greatly. And what happens to the fox if the mouse population goes down? What happens? Foxes will have to eat something else, or they'll have to leave, or they'll have to die. And what happens to the population of the mice if the fox population goes away? Or if the mice population goes up, foxes will increase in number. So in this way, we have a sort of back and forth. So population growth follows the following formula. Population growth equals the number of births and immigrations minus the number of deaths and emigrations. Emigration is leaving. So this is to leave, and then to enter. So entering ecology, entering the ecosystem or leaving the ecosystem. If the emigration goes up and the other factors stay the same, then the population decreases. If births go up, other factors stay the same, then the population increases. So if we think about that reindeer example we had earlier, at the beginning, we had a little bit of immigration of some reindeer, and then we had lots of births with minimum deaths. But then as food became scarce, the number of deaths increased until the population was gone. If a population is stable, the population growth is zero. The number of births and immigrations is going to be equal to the number of deaths and emigration. This is called a steady state or a population equilibrium. Love that word, equilibrium. So there are two types of populations that we must consider in this case. There are open and closed populations. So most populations are subject to all four of these factors, where individuals are born and died and individuals can come and go. These are what is known as an open population. So open population is one. So this is a population with emigration and immigration. Meanwhile, a closed population is one where the populations cannot enter and leave. So this is for example, like islands or game reserves, experimental settings, some valleys might be that case. If we're talking about a population of organisms that can't leave very easily. You could also have like a closed off lake or something like that, mountaintops, somewhere where there is no way to come and go. In this case, the population growth depends only on birth rate and death rate. And so this is called a closed population. No immigration, no emigration. So if you were a salmon farmer, you might try to make a closed population because you want to keep your salmon herd uh, a in a one genetically similar. So you'll actually cut off your salmon population from the rest of the wild salmon, so that your salmon are only are in a little bay or whatever, and they're cut off from the rest of the water. They can't enter and leave. And this will help you keep your salmon population genetically similar, so that you can control for the traits of that population. When humans were in small local population, each was open. When we look at the population of the whole world, we see that it's a closed population. No one moves to another planet. No new people arrive from other planets. Changes in the total human population, therefore, depend only on the death rate and birth rate. We currently have about 2.7 times more births than deaths. I would like to check that number because I bet uh, uh, global mortality rate. Our world and data. I'm just checking it up. I've got it open here. Birth rate versus death rate in the world. In I would like to see, here's 2016. Data, I got the chart up. Okay, well there is a little date, a little diagram we can play with here. It is interesting. I could find Canada or North America. Cayman Islands, here's Canada. Canada. We got deaths and births is Y, so it's 10.8 to 7.5. So 10.8 divided by. So in 2016 it was 1.44, but that was Canada. In other countries like Africa, the number is much higher. So 48 to like 5. So I'd like to do average annual change. No, that's not what I wanted. Okay. I'll send you guys this link just in case you want to play with it. And you can check things out as much as you like and see where I would like to see the average. Where's the average? Oh, our world in data. I got one more here. Let's see. 2015, unit projection, births projected, 140 million. How many die each year? Okay, 140 to 57. There we go. Okay, 140 divided by 57. There you go, 2.5. Okay, so pretty much the same number. Well, that was pretty boring. Okay, glad I did all that work. Yeah, so right now in 2016, I calculated 2.47. So yeah, I guess we're on a low a little bit there in 2016. 2020 is going to be a wild year for that as well. So we'll have to wait till that comes out. But this will be a very strange year. So this human population is not at equilibrium technically because we are still growing. So this implies that the human population is still growing. Are we reaching our carrying capacity? Our global? That's a question we should maybe spend a little bit of time thinking about. It might be a sad question to think about too much. But you know, we'll keep it in mind. Okay. Measuring animal populations over time. A common practice for ecology is to measure the changes in population size over time. This is often using a mark and recapture method to measure the numbers. You can't capture all the animals. There's just too many to do that. But you can capture a whole bunch of them. You can give them some markings. These are usually little tags you put on their ears, and then you send them back out. And then later, when you capture a bunch of animals again, you see how many of them were marked. And based on how many of the ones you captured were marked, this tells you how many more there might be out there. So for example, if you mark 10 voles and a week later you catch 20 of them, but only one of them is marked, you can assume that that for every 10 voles you catch, so if there are 10 marked voles, these are supposed to be fractions. That's why I'm having some trouble reading this. Here. So if there's 10 moles that you captured out of the total number of moles, and one of those moles out of the 20 moles you catch, it was marked, then you can do some cross multiplication to find out that this would be 200. 10 out of 200 moles are marked. This result can be graphed and several interesting patterns can happen. So this is the population graph section, which is always fun. So population graphs, this is a graph of a young population. The low part of the curve shows where there are very few individuals, and the population increases slowly at first, slow increase. But once the population grows a bit, more and more individuals get to the reproducing age, and they also start to have a higher chance of interacting and to reproduce. So the population grows suddenly. Now, at this stage, we suddenly have a competition for resources, and so the population starts to be in competition, and the rate of growth slows down quite a bit. So this is, I'm going to do a little bit of cleanup here, and I'm going to write it out. So here we have the early part where there are few individuals, and few births. Maybe I'll convert that to a text. And so then in the middle section, we have many individuals and many births. And in the last section up here, we have competition between many individuals more deaths. So as the population gets bigger, we get more competition, and that equals more death. And emigration, I guess. Sometimes some people populations will leave. When you have reached the population, in fact, if you were to able to zoom in on this section up here, if we zoomed in, zoom in, you would notice that this population, as it straightens out, it's actually little lumps of ups and downs depending on how long you watch it. So in this example, the population has reached a limit. So this dotted line here is the carrying capacity, which we could also probably draw in around here somewhere. So that would be our carrying capacity here. And so the population is sort of stuck around that carrying capacity. Some years there's a couple extra individuals, some years there's a few less, but in general, the population is able to support the ecology, the ecosystem is able to support the population, and the population just varies a little bit at a time. Sometimes population bit low, sometimes higher. Limits in the carrying capacity for the region are represented in the dotted line. And so this is the maximum population that the area can support for long periods of time. Now this is excluding any random events or huge changes. So if something happens, like something bad happens, then that would be like a catastrophe or a drought or something like that. Then we could have a sudden change in that equilibrium. So we can call this one equilibrium. And then early growth. Okay. Now, if a population exceeds the population, this is called a crash. So if you exceed this carrying capacity for too long, then the population could actually use up too much resources. So using up too much resources, and now the actual environment around them has run out of the resource that they need. And so this is population crash. The population actually might right here see that we're actually reaching zero, so that means we're dying out. So this is bad news. So the population, the environment cannot recover. So the environment from the resource. So this is that reindeer population we talked about earlier. So see reindeer example above. Um, so this is like that reindeer population on the island, right? They go on the island, they start eating the lichen. Lichen are really slow at growing, and mosses are slow at growing. So when they eat a whole bunch of them up, then suddenly there's none left, and there's not enough left to actually for the lichen and the mosses to grow fast enough for that population to have food for the next generation. And so very quickly, there's not enough food, not enough food, and after many years of not enough food, the population just starts to shrink very quickly until there's not enough individuals to reproduce even if the moss or lichen population is climbing again. Okay, this last example shows two populations at once, foxes and rabbit. The fox population here, right, is down here. This is the rabbit population. Here you can see that early growth phase. So here's our growth, right? Population growth. And as the population grows, suddenly there is a slightly delayed, but a later delayed, there is a population growth in the foxes. So we can call this example the predator prey growth cycle. And so as the population of rabbit increases, then the population of fox increases. When the population of fox increases, then there is a sudden drop, right, of a decrease, population decrease from that increase in foxes. And then with that population decrease, you have a responding decrease in the foxes. Response. And then and now that the fox population is low again, you're going to have another growth cycle, which will lead to another growth cycle in the foxes forever until something interferes, like an invasive species or something. The rabbits are very low, but they have lots of food. They will go back up soon, etc. And then they go up and down and up and down. Notice that the fox line is always lower. There are far fewer foxes than rabbits. The rabbits' peaks tend to be ahead of the foxes. It takes a while for the fox population to respond, I like that word respond, to the extra rabbits. And with that, we are at the end of ecology. So I will leave you with the last 30 minutes of class to work on your final assignment. I posted it yesterday. So you can work on that final ecology assignment. It shouldn't take you very long. It is very short, I think. So that will be your homework for the weekend. It is a long weekend, so there will not be a stream tomorrow, although I believe that Matthew is planning to post a physics lesson in case you finish all of your work and you want to watch more physics lessons, then those will start to be posted. And then from this week on, Matthew will be in charge of posting And I won't do much for this. I'll probably spend the time catching up on some marking and getting you guys some of your marks back and things like that. So we will be off the stream for a little while, and then I'll let you know in classroom when we're going to get back into these streams. And we'll see there. See you at that time then. Okay, talk to you later.